Now, it's possible to add sines and cosines together as long as they have the same values, such as omega t here and here. In this case, a sine omega t plus b cos omega t is equal to r sine omega t plus phi. And the r value here is given by a squared plus b squared square root of, and the phi angle here is given by the inverse tan of b over a, which is very similar to what we did with complex numbers converting from rectangular to polar form. And what we're going to do is we're going to apply that to what we have here and come up with an equivalent single sine function, such as r sine omega t plus phi. And once we do, we're going to then compare that to what we would get from Desmos for this wave and the one that we're going to actually come up with as a combined waveform. Now, if we apply this formula, we can see that the coefficient of sine t here is 1, coefficient of cos t is 1, so the r value here is going to be the square root of 1 squared plus 1 squared, which is the square root of 2. Also, the inverse tan will be this over this, b over a, which will be 1, where phi is therefore 45 degrees. So our new formula is going to be y equals square root of 2 times sine of omega t plus 45. And what we're going to do is we're going to use Desmos to take a look at this curve, and we're going to compare it to this curve to make sure they're exactly the same. And if they are, this is indeed the formula that we need. Now, what we've done to plot y equals sine t plus cos t is we've gone up here, clicked on this, we set our x-axis here to be minus 50 and all the way to 430 with a step size of 45 degrees. And we made sure we set degrees. And that's why we get this curve here. Now you notice that this curve starts at minus 45, goes through here at 135, goes through here at 315, ends up here at 405 for this peak. Now, if we want, we can say, okay, let's turn this on and see if our equation is the same. And if we see it looks identical, and if we take this out, it is identical. Both of them are exactly the same curve. So the formula that we've got here is exactly the same as the formula here where we have sine and cos together, but it's all written as one sine function here. Now, one other thing we can do is say square root of 2 sine t plus 45 degrees equals negative 0.5. What are the points of intersection? Now, just by clicking on here, you can find that this one here is 155.7. This one here is 294.3. But how do we work that out ourselves? Let's take a look at how we would go about doing that with what we know. We know our period is going to be 360 degrees because we have 1 here. 360 over 1 gives us 360 degrees. So all the way from minus 45 up to 315 is 360 degrees. Now our equidistant points here are going to be 360 over 4, 90 degrees between each one. C here, as we saw here, is 45 degrees. And so our phase shift is going to be minus 45 over 1 here. So it's just minus 45 degrees. And we can see that indeed we have shifted 45 degrees to the left here to get minus 45. Now we set root 2 sine t plus 45 equals minus 0.5. And so sine of t plus 45 is equal to minus 0.5 over root 2. T plus 45 is equal to the inverse sine of minus 0.5 over root 2. And that works out to minus 20.7. So when we say t plus 45 equals that, minus 20 minus 45, which gives us a total of 65.7. And 360 degrees over here, subtract the 65.7 is going to give us this point here, which is 294.3, which is one of the points that we saw before. If we subtract from 315, which is where it crosses the line here, to 294.3, we can see that there's a 20.7 degree difference here. That means that here from 135 to here is going to be also a 20.7 degree difference. So we take 135 and add 20.7, we get 155.7, which is our other point here. And we've got all the things that we need to know, that square root of 2 sine t plus 45 equals minus 0.5. These are the points of intersection here.